Self-care? Who is she?
All right, you guys, 12:50. Let's go ahead and get started. What I want you guys to do is get out your sheet. The sheet that rolled out acid-base regulation. Let me go ahead and put that on the document camera so you know what I'm talking about. All right, so it's this chart that I want you to take a look at. Julia's passing out a case study right now on Into Thin Air. It's a case study on high altitude. So here's what I want you guys to grab. This is the chart. For your exam, I actually want you, I'll give you this for the exam, and it'll be like a mock case study. All right. Yes. Yeah. So there already is, just like in past exams, the equation sheet. Okay. So the equation sheet is already on Moodle. It'll state equation sheet for exam 3, and then I will give you this chart as well. Okay. I'll put that on Moodle, and this will help you kind of think through a case study, for instance, okay? All right, so let's take a look at this Into Thin Air, okay? What I want you to do is go to part 4 and take a look at this. Mark, the case study is about a guy who is climbing a mountain, right? This is Denali. And he's at pretty high altitude, and then all of a sudden he goes into respiratory distress. Okay, respiratory distress. This is called HAPE, H-A-P-E, which is high altitude pulmonary edema. Okay? All right, so this is what the whole case study is about. But let's take a look at this, okay? I want you to use your chart here, and let's decide, this kind of goes along with what we've been talking about before. Here's his blood levels. Let's decide, first of all, whether if he has acidosis or alkalosis. Use your chart. You can work in groups. Let me know what you think. You can just raise your hand. It's more of a class discussion. Okay? The normal values are on the right. Mark's value, he's suffering from HAPE, high altitude pulmonary edema. He's very sick, can be lethal. So you guys have to let me know what you think. This is a typical question that I would ask you for an exam, and it goes along with this particular case study. Not until next Wednesday. So the respiratory essential calculation sheet isn't due until next Wednesday. This one will be due on Monday, but you'll have time to work on it on Monday. Okay? So just take a look at it over the weekend, answer as many questions as you can, and then we'll talk about it on Monday. Yes? Yes, I do have extra copies of the chart today. The chart, I think there were 5 extra copies. Let's see here. Yes. Here you go. Anybody need another copy of the chart? Okay, I just have a few extra copies. 1, 2. There you go. I only have 1 extra.
Is it on Moodle?
You have 2 over there? Okay. Oh, those are for the case study. These are yeah, that's okay.
Is it posted on Moodle?
It is posted on Moodle.
Okay.
Okay. Sorry about that.
Thank you.
All right, so here's his values. What do you guys think? Does Mark have acidosis or alkalosis? he has pretty profound acidosis, right? His pH, his blood arterial pH, is fairly low, 7.23. Normal is 7.38 to 7.44, so it should be right at 7.4. All right, so here's the tricky part. I know he's at high altitude, but I want you to look at this carefully. All right? Does Mark have a respiratory acidosis or a metabolic acidosis? Take a look at his values. Read your chart. All right, what do you guys think? Who wants to take a stab at it? Metabolic? Anybody disagree with metabolic acidosis? That's actually right. Okay? You might think because it's high altitude and usually at high altitude you have respiratory issues. This is technically a metabolic acidosis. Okay? So why might that be? Why might that be? There's a respiratory compensation, but why do you think?
He has a really low bicarbonate.
He has a very low bicarbonate, so it doesn't have a lot of blood buffer. That is absolutely right. But what else? What else? What's the cause of the acidosis, do you think? So he has pulmonary edema. It's kind of like pneumonia. Water is accumulating in his lungs. Okay, so he's probably not getting a whole lot of oxygen into his blood. And you can actually see this here, right? His arterial oxygen is very low, right? So what do you think? He's not getting oxygen. Oxygen isn't perfusing his tissue. This is a hard one. Why don't you take a couple minutes and talk to your neighbors as to where the source of the acidosis is coming from.
Just saying, big fancy. She's gonna
All right, who wants to take a stab at it? What do you guys think? Anybody have any ideas of where this acid is coming from? Do you need a hint? Okay, what about what you've learned from skeletal muscle? Yes. I would say as your muscles are working and not quite fatigue, but you have a, yes? Exactly. Okay, so there's not oxygen, right? Oxygen isn't getting to the tissue. So the muscles are going into the anaerobic pathway, right? And they're using glucose, but they're actually, and they can fatigue quicker, right? That is a part of it, you're right, because it's not generating as much ATP. But it is going to build up a lot of lactic acid. Okay, so lactic acid is building up in the bloodstream and it's causing the acidosis. What is the body's compensation? Take a look at your chart again, right? Take a look at this chart. How is your body going to respond to the metabolic acidosis? You're going to hyper or hypoventilate? Hyperventilate. So that's the respiratory compensation here. As you hyperventilate, you're going to blow off CO2, which is going to cause your CO2 levels to go fairly low, right? So let's take a look at it. When you look at Mark's CO2 levels, they're fairly low. So this is low due to the respiratory compensation. So you can say something about this now. You can say Mark has metabolic acidosis and his CO2 levels are low because the respiratory system is compensating for the metabolic acidosis. Okay? All right, good job, you guys. So now that kind of helps you, but this is also a great case study related to the acid-base regulation that we were talking about on Wednesday. Okay? All right, so take a look at this in a little bit more detail over the weekend. We may have some time at the end of class to go through it. I will have this chart for you during the exam, so it should be fairly easy to answer those questions, but you know, it's still a little tricky. I want you to get some practice on it though. All right, one more example. I want to make sure that you guys still understand the respiratory compensation. When individuals, patients have diabetes mellitus, right? Diabetes mellitus. They have some issues with insulin, right? And high blood glucose levels. What happens is the glucose can't be taken up by the muscle cells, right? So the muscle actually uses proteins and fats for energy instead of glucose. You guys, that makes sense, right? All right. In that case, it starts to break down muscle and fat, and patients can develop what's called ketoacidosis. All right? The breakdown of muscles and fat causes an outpouring of acid, right? And it happens with starvation, ketoacidosis, but it also happens with diabetes mellitus. What would be the compensation? This would also be a metabolic acidosis. You would actually get the respiratory compensation, right? When we're talking about diabetes specifically, patients come in sometimes unconscious with something they call Kussmaul's breathing. See how it's spelled here? Kussmaul breathing. This is the respiratory compensation due to the metabolic acidosis because they're diabetic. It's called diabetic ketoacidosis. So let me just show you what it looks like.
All right, like this little guy actually presents here. He's a known insulin-dependent diabetic, and he's come in with a pH of like 6.9. He's actually got a little bit of probably a dental abscess that's kind of kicked him off here, but his breathing is really what we kind of call Kuzma breathing, and when you smell his breath, it basically has a very sweet kind of a acetone, ketone sort of odor to it. So he's getting getting a little fluid bolus, 20 per kilo, and then we're going to also start him at 0.1 units per kilogram per hour of insulin, and he's going up to the intensive care unit. And his his initial, like I said, his initial pH was 6.9 in that ballpark. So his mom knows these videos end up on YouTube, and she's okay with that, right, Mama?
Yes.
Okay, all right.
All right, so he's pretty much unconscious, but his breathing, this is uncontrollable for him. This is his body's compensation to the metabolic acidosis due to diabetes. Okay, so just some really good case studies here to really help you with how your body responds to changes, disturbances in pH. All right, anybody got any questions so far? Just wanted to touch upon that before we started up with respiratory again. Okay. All right, so let's go ahead and start with the lecture today. Here's where we left off with the respiratory system. I want to make sure that you guys have this information. Okay, like I said on Wednesday. Oh, a couple announcements before I get started. I almost forgot. I am recording this lecture today, you guys. I'll put this on Moodle so that you'll have access to it. There is a formal review session next Wednesday, right after class, between 2 and 4. You can come in and out, if you can only stay for an hour, that's fine. I will record it. I can't do it on Friday because I have guests coming in from Belize on Friday, okay? That brings me to another thing. I will offer some extra credit if you go to the seminar on, and so, I know you guys, some of you guys have been asking me about extra credit. So I will offer 10 points extra credit if you want to go to this particular seminar, especially if you're interested in wildlife veterinary medicine, okay? So, so Dr. Isabel Paquet Durand will be here in 365. I'll also put out an email with a flyer. 365 Hackard Hall at 2 o'clock on Friday, okay? So you guys are welcome between 2 and 3. Next Friday, yeah, not today. All right, you guys. So the review session is Wednesday between 2 and 4. That seminar is next Friday between 2 and 3. Yes, question? Nope, just, I'll have a sign-up sheet when you walk in. Yeah, and you can just write your name. Yep. All right, so as I said on Wednesday, you guys, Wednesday I said this is one of those charts that will be on your exam. All right, I'm telling you right up front, like I told you several times. The area that most students miss on an exam is they forget about this bar right here. You're going to have to label, I'm just telling you right up front, you'll have to label the conducting zone and the respiratory zone. Can anybody tell me what the difference is between the two? What is the difference between the conducting zone and the respiratory zone? Yes.
There's no gas exchange in conducting.
Perfect. There's no gas exchange in the conducting zone. Okay? Really, 99% of the gas exchange occurs in the respiratory zone. All right, so let's go through it. You'll have to label these two bars. Trachea branches into 2 bronchi, and then into various bronchioles, and then it keeps branching into terminal bronchioles. From there, it continues to branch into respiratory bronchioles. Now, this is where gas exchange starts to occur. About 500,000 respiratory bronchioles. Then they branch into alveolar ducts and alveolar sacs. You have about 8 million alveolar sacs in each lung. Now, the bronchioles have a lot of smooth muscle cells that surround each of these airways, and they can constrict or dilate to control the flow. That's called bronchodilation and bronchoconstriction. So let's focus in first on the conducting zone specifically. What are some of the functions of the conducting zone? It provides a very low resistance pathway for airflow. And again, resistance is regulated by the contraction of those smooth muscle cells. Also, the conducting zone defends against microbes, toxic chemicals, and other foreign matter because, as we talked about on Wednesday, they possess cilia, those little projections, hair-like structures that captures mucus and microbes. And when you cough, that's part of the mucociliary clearance. And within that mucus, there are, like I said, immune cells like macrophages that actually chew up and eat up those microbes. The conducting zone also warms and moistens the air. This is kind of interesting. I talked about this in lab already. Because it warms and moistens the air, especially in the wintertime, the volume of air that you breathe in is not as great as the volume of air that you breathe out. Because it's warmed and moistened, the volume of air that you breathe out is much greater than the volume of air that you breathe in, especially in the winter. Okay? And then also the conducting zone is responsible for sound, phonation, through the vocal cords. All right, so now let's go ahead and talk more about the respiratory zone. Okay, so the respiratory zone includes the respiratory bronchioles, the alveolar ducts, and the alveolar sacs. Okay, so if you take a closer look at this, right, deep within each of the lungs, you have these alveolar sacs. Okay, now this is a little misleading. These diagrams look less like a cluster of grapes. They look more like, I can kind of skip ahead a little bit. They look more like this, right? They look more like craters than they do grapes. But I like this diagram in that you can see that each alveolar sac has a very rich blood supply. You can see those pulmonary capillaries. They really are closely associated with each of the alveolar sacs. And in the respiratory bronchioles, you can actually see a lot, terminal and respiratory bronchioles, you can actually see a lot of smooth muscle cells that can constrict or dilate to cause bronchoconstriction or bronchodilation. Okay? So again, this is where all the gas exchange occurs. It's really important to realize that. So let's go to the next slide here. We've already seen this before when we talked about the main parts, the upper and lower respiratory tract. Now I'm going to start with the second bullet point. First, we're going to talk about alveoli and its structure and some of the cell types associated with it. Then we're going to get into ventilation, and we'll talk about the pleural sacs. There's a sac that surrounds each of the lungs, just like the pericardium. You guys remember the pericardium from the heart? Yeah, lungs also have a sac that are associated with it. So you can actually see, here's a good diagram of the alveolar sac and the pulmonary capillary that's very closely associated with it. This is again where all the oxygen and carbon dioxide are exchanged. And then take a look at this. You can actually see there's different cell types. One is called the alveolar cell type number 1. And then there's an alveolar type 2 cell. Okay? Then you can see these capillaries and macrophages that are closely associated with those alveoli. So again, if you look at an electron or a scanning micrograph, you can actually see this is more of how the lung is organized. I'll start by looking at this panel first, okay? And then we'll go to the actual image. So you can actually see the terminal bronchial, respiratory bronchioles. These are what's considered the alveolar duct. And then, like I said, it's more like craters. These are the alveolar sacs. So this circle right here, this is an actual image, a scanning electron micrograph of the alveolar region. This is a duct. The D is for duct. And the A is for the alveolar sac. Okay, so we're really concentrating on anatomy right now. So here's another diagram. You can see the respiratory bronchiole here, alveolar ducts, and the alveolar sacs. So the alveolar and the capillary walls are super thin to allow for diffusion of gases, right? And the reason why there's so many of them, 8 million of them, is because it really increases the surface area to maximize exchange between the air and the blood. And one more time, you can actually see the alveolar type 2 cells here, and then the capillaries with the red blood cells. Okay, so in a minute we're going to talk about a very special molecule that's secreted specifically by the alveolar type 2. Not by the type 1, but the type 2. It's actually, it's kind of like a detergent. It's a mixture of phospholipids and proteins called surfactant. Okay, we'll talk about surfactant in a minute. It's kind of like the bubbles that you blow. You know, as a kid, you had the bubble with a little wand, and you could blow bubbles. Surfactant is a detergent like that, but it helps to hold the alveolar sacs open, and it increases their stretchability, makes them more compliant. We'll talk about that, what that means in a second. All right, keeping with the alveolar sacs, I also want you to realize that this is really diffusion, motionless air. Okay, so the terminal bronchioles and the respiratory bronchioles, you can see that there is flow of air, convection. But then once you get into the alveolar sacs, diffusion happens through mainly motionless air. And there really is a dilution effect. There's going to be mixing of stale air from the previous breath and fresh air from the most recent breath. Okay? So it's not really efficient, not like birds. So birds are a little bit different. I want to just touch upon birds. Most of what we talk about in this class is physiology, but it is kind of nice to compare and contrast sometimes, especially in this case with birds. They have a very efficient respiratory mechanism. So I'm going to just show you this particular, I think this is pretty cool. All right, so here's a typical bird lung. Let's see if I can blow this up a little bit. Okay. Sorry, there should be a better way to do that. Plus, nope, not working. Okay, so here is a bird. You can see the trachea. Now, birds have lungs, like we do. Here's the lung in red, but they also have what's called posterior air sacs. These are closer to the tail region, and anterior air sacs. Okay, so here's how it works. Air, actually, you need 2 breaths. Air's brought into the posterior first, and then the lungs. And with the second breath, It's forced into the anterior and then out. Okay, so it takes 2 breaths for that to occur. And this is just giving you a diagram now. These are the anterior air sacs, this is the lungs, and this is the posterior air sacs. So let's go through it one more time. You can actually see it's giving you the anatomy. Here's with breath 1, bringing air into the posterior air sac. Okay, that's with the inhalation. And then exhalation forces that air into the lungs. With the second breath, it forces the air in the lungs to the anterior, right? So the air that was in the lungs went from the lungs to the anterior and then out the trachea. So again, it takes 2 breaths. Does anybody notice what the advantage of these types of lungs are? If you kind of think about what I just described with mammalian lungs and that dilution effect, how is this an advance? Yeah.
Decreases the amount of stale air.
Exactly, right? So this actually sets up a system where there's unidirectional flow. There's never mixing of fresh and stale air. So you're always getting completely fresh air into the lungs, which is pretty cool actually. So this is actually kind of cool. This allows birds to fly over very high altitude. They can literally fly over Mount Everest. We couldn't do that. We would pass out, which is why a lot of people have to carry air tanks when they go up to that high altitude. Okay? Pretty cool. All right, so. Okay, so we're continuing on, you guys. Let's talk about surfactant and what that is right now. All right. Surfactants are, like I said, a mixture of phospholipids and proteins. And they reduce the surface tension. Anybody know what the surface tension is in water? The surface tension is if you put water in like a beaker or a flask, you would notice that there is what's called a meniscus. You guys remember that probably from high school, right? That actually is called the surface tension. And a lot of times it is a cohesive force that allows for, say, water bugs, to walk along that surface. So what surfactants do when they squeeze in between the molecules right at the air-liquid interface, they reduce that surface tension by disrupting those cohesive forces between the water molecules. And what that does, I'm going to introduce the idea of compliance. It results in an increase in lung compliance, which means compliance is the stretchability. Now your airways the alveolar sacs are more stretchable. And it decreases the force that's needed to inflate the lungs. Now, we'll talk about this in a minute, but surfactant synthesis doesn't begin until late gestation in utero. You guys have heard on the news, you've heard stories about babies that are born around 26 to 28 weeks. The issue that they usually have is they have lung issues. And that's because babies don't produce surfactant until after 26 weeks. Okay? So let's dive into exactly what compliance is. I'm only going to go through the top part. We're going to talk about transpulmonary pressure in just a minute, but lung compliance is the measure of the lung's stretchability. And I'm just going to go through this up here. Compliance is really telling you something about the relationship between volume and pressure. So if you have high compliance, it only takes a little bit of pressure to make large changes in volume. That means that the airways are very stretchable. You just have to use a little bit of pressure, and that can translate to very large changes in volume. Low compliance is the opposite. So it's really the difference between something like this. You know, when you blow into, let's just say, a baggie, a paper bag or just a baggie, right? It doesn't take very much pressure. You can open up that bag pretty easily, right? That would be high compliance. But let's take a balloon that hasn't been stretched out yet. You guys ever notice you try to blow that up and it's really hard? You have to really, create a huge pressure, and really the volume doesn't even change all that much. It just kind of opens up a little bit. That would be low compliance. Okay? Pretty good? You guys, that gives you an idea of what compliance is? Okay. We'll revisit this one in just a second. All right, so this is a nice summary slide. Pulmonary surfactant is a mixture of phospholipids and proteins. Remember, it's secreted by the type 2 alveolar cells. It lowers the surface tension, which increases the compliance. And it has more of an effect on the smaller alveoli, and we'll talk about how it stabilizes it. So, you guys might not know this, but when you sleep, right? You sleep all night and you're in a horizontal position. A lot of times your alveoli, there's a certain percentage of alveoli that just collapse just because you're sleeping. So it might be a good idea to, when you wake up in the morning, just stand up and breathe in deeply, because the stretch of those alveoli will produce surfactant, and that helps to get those airways open, right? It's a nice idea just to breathe in deeply right when you wake up, okay? And just remember, the production in the fetal lung occurs in late gestation. That's why premature babies actually have a lot of lung issues. All right, so going along really nicely. Now it gets a little complicated. Need to introduce the idea of the law of Laplace. I'm not French, so I'm sure I butcher these French names, but law of Laplace. Capital L-A, capital P-L-A-C-E. And what that says, it's giving you an idea, this diagram, the difference between if there's no surfactant and if there is surfactant. Okay, so this is saying pressure, this is giving you the relationship between pressure, surface tension, T, and the radius of the alveoli. So in this first case, when there's no surfactant, the surface tension in A, the larger alveoli, is equal to the surface tension in B, which actually presents a problem. If you plugged in these if you calculated the pressure in A and you calculated the pressure in B, because the surface tension is equal but the radius is not, the pressures are going to be very different. Okay? So the radius of the smaller alveoli is going to have a much higher pressure. Pressure B is going to be much higher than pressure A. That creates a problem because air is always going to flow from high pressure to low pressure. So what's going to happen, since this is higher pressure, the air is going to flow from B into A, and you're going to get alveolar collapse. You're going to get a certain amount of alveoli that are going to collapse, and that's going to increase dead space. You guys remember dead space? Dead space is when there's no gas exchange. That's going to increase alveolar dead space. However, when surfactant is on board, because of its unique properties, the surface tension in B happens to be lower than the surface tension in A, just because of the unique properties of surfactant. What that seems to do is it equalizes the pressure so that there's no alveolar collapse. By reducing the surface tension of water in B more than A, surfactant helps to prevent alveolar collapse. So that keeps dead space at bay, kind of. It doesn't increase the dead space, alveolar dead space. Okay, so I do have a couple of top hat questions. Let's go ahead and get your top. Okay. Top hats. Okay, so what I'm going to do is, this is a review. We're going to go back to the kidney just for fun. All right, so I know you haven't really studied this yet, but let's see how you guys do. Why is the following true? Creatinine clearance, if you use the clearance equation, right, and you calculate creatinine clearance, why are you actually calculating glomerular filtration rate? Is it because creatinine is freely filtered but not secreted or reabsorbed? B, creatinine is freely filtered and strongly secreted. C, creatinine is freely filtered and strongly reabsorbed. Creatinine is not excreted. Or D, none of the above. Why is the following true? When you calculate creatinine clearance, you're actually calculating glomerular filtration rate. You guys can talk to your neighbors. All right. How many of you guys need a little more time in here? Pretty good? All right. Okay. I'm going to go ahead and, oh, we still have some. Go ahead and pause this. And the correct answer is A. Woohoo, let's see. Okay, pretty good, you guys. 82% of you guys got that right. So remember, creatinine is just filtered. It's not secreted or reabsorbed, so whatever is filtered ends up in the urine. That's why it's a really good marker for flow, right? Glomerular filtration. Okay, perfect. All right, let's go to the next one. Okay, let's see here. All right, so this is the one that pertains to today. Hopefully you guys were awake. Surfactants. Surfactants decrease surface tension and increase lung compliance, or do they increase surface tension and decrease lung compliance? C, decrease both surface tension and compliance, or D, increase both surface tension and compliance.
Sorry, you guys not call them decoms. Big fans.
All right, how are we doing? Anybody need a little more time? All right. I'm going to go ahead and pause this. And the correct answer is A again. Nice. 94%. You guys are awake. That's awesome. Good job for Friday, right? Friday afternoon after lunch. Sweet. Okay, so you got the idea. You're understanding what surface tension means and lung compliance, which is fantastic. Let's go ahead and move on. Let's now start talking about, I know we only have a few minutes, but at least I can give you guys the anatomy. Okay, so here's how the lungs are organized. You actually see the lungs are surrounded by a sac. This is the pleural sac. Now, always the parietal is on the outside. The parietal pleura is on the outside, and the inner membrane closest to the organ is the visceral pleura. Now, in between, you actually have this nice fluid layer. There's fluid in between there. And then the heart sits more on the left-hand side. Okay, so here's a fluid-filled balloon, you guys. Your hand is supposed to be simulating the lung. And as you just put that into the fluid-filled balloon, this is supposed to represent the pleural sac. So there's a really, I'm going to say stupid, because it's so stupidly simple. So I'm going to play that for you. I know, it's so funny. Okay, so here it is. Don't blink or you'll miss it. Pleural membranes. Fluid-filled balloon, lung. That's it. Right? You want me to play it one more time? There you go. Why they even made that animation just cracks me up. All right. Okay. All right, so let's talk. Okay, here's the idea, though, with this. You can see that the parietal pleura is actually very closely associated with the thoracic cage, the thoracic wall. The visceral pleura is very closely associated with the lungs, okay? So, and then there's fluid in between. Think about it this way. If you've ever played with microscope slides, right? Just like, and you put a little fluid in between the microscope slides, you can easily move them up and down. So the pleural sacs help with buffering, right? But if you try to pull them apart, it's almost impossible, okay? They can slide up and down easily, but if you try to pull them apart, you can't do it, okay? So when the thoracic cage opens up, is pulled out when you breathe in, it pulls the lungs open as well, okay? So the space inside the lung is filled with air. The intrapleural fluid is found between the lungs and the thoracic wall, and movement of the thoracic wall by skeletal muscle drives the ventilation cycle. This is where we'll start. We'll talk about inhalation and exhalation on Monday, you guys. Work on your into thin air and your essential respiratory calculation sheets, and I'll see you on Monday. Have a good weekend, you guys. Yeah.
So I thought it was while you were talking about why is there a cloud
It is, you know, I think it has.
I laughed so hard.
In the micro.
Was it good? Oh yeah.
Yeah, because you're still.
No, not badly.
Yeah.
I was
Yeah, I think it has more to do with what's in your stomach.
Do you know when we're going to hear back about the story?
Yes.
Because,
Yes.
yeah.
Keep going with what you planned. And I've already contacted a few folks. So I will get to this very soon.
Okay.
And if you guys have some specific questions, email me over the weekend.
Okay.
And what is the name of your guys'
I
group?
don't know the group. We just had the same.
Oh, okay. Oh, okay. What is the name of your group? Do you have it?
Well, we were a muscle group. We did like
Okay.
a song parody.
Oh, yeah. Okay. And you?
I don't remember. It
Okay.
was something about neurons.
Okay, all right. I'm going to get to it.
That's
Yes,
okay.
okay. Thanks for asking, you guys.
always.
I just have two.
Yes.
So you had said that the conducting zone have cilia because they defend and capture mucus, but that's also true for respiratory, correct? Because I
That's,
wrote that down.
yeah.
for both
So
of
the entire respiratory tract, although it's not so much in the alveoli, you don't really have cilia in the alveoli. It's mostly in the bronchioles,
Which is the conducting zone.
conducting and some of the respiratory zone.
Okay,
The
because I
respiratory
wrote
bronchioles, yeah.
clearance.
Mm-hmm.
Does clearance have more, or I mean,
Yes. So what it is
I don't know,
is So mucociliary clearance
Yep.
is a way you have epithelial cells and mucus secreting cells
Okay.
that capture microbes. So imagine, right? And they have macrophages within that mucus.
Okay.
And then when you start to cough, or you can kind of feel it,
Mhm.
the cilia move the mucus towards the trachea.
Okay.
And then
Yep.
you cough it out.
Yep.
That is a mechanism called mucociliary clearance.
Okay.
And it's mainly in the upper respiratory tract.
Which is
Yeah.
the conducting zone.
That is the conducting.
Okay.
Yes.
We'll just
Yeah.
well, whatever. Okay.
Yeah.
And then my other question was just kind of going over what
Yes.
happens if you increase and decrease compliance and how that correlates to lung volume and pressure.
Yeah. So if you have surfactant on board, imagine at first, let's imagine you don't have surfactant on board.
Okay.
It takes more pressure. You can positive,
so
to
that's-
open up the lungs.
That's correlating to
Mhm.
the law here.
Yes, yeah. So in this case,
Yeah.
this is actually talking about alveolar collapse.
Okay.
When you have pressure differences between alveoli, because they're not all the same size,
Yeah.
the smaller ones are going to tend to collapse into the larger ones.
Okay.
But surfactant, because of the unique properties, surfactant actually lowers the surface tension more in the smaller than the larger.
Okay.
And that tends to equalize the pressure, so there's no airflow.
Okay.
And you don't get the collapse, so that you
No alveolar.
yeah,
collapse.
exactly. So we're going to also talk about this again and apply it to the lung as a whole. Okay, so let me give you an example. With cystic fibrosis, right, people that have cystic fibrosis, they have so much scar tissue in their lungs,
Okay.
it takes more transpulmonary pressure to open up the lungs than normal people. So they have to really breathe harder
Okay.
to open up the lungs. That would be a
Okay.
low compliance. Takes more transpulmonary pressure
Okay.
to increase volume.
Okay.
Okay.
Decrease compliance to increase pressure.
Right. With emphysema, it's completely the opposite. Okay, so they have lost, the lungs are like a balloon.
Mhm.
When you breathe out, it's kind of like, it has a recoil. Like a balloon that you blow up, if you
Yep.
let it go,
Yep.
it would just, there's a recoil. With emphysema, they've lost that recoil. So
Okay.
it's super easy to blow up the lungs. Super easy.
Okay.
It takes very little pressure for them to open up their lungs.
And you're saying opening meaning compliance, stretching.
Yes.
Yes.
So
Okay.
it's super
Yep.
stretchable.
Yep.
you would think that would be an advantage
Yeah.
with people with emphysema.
Mhm.
The problem is there's no recoil, so
To go
it's,
back.
they can't get the air out.
There's no pressure to
Yes.
get it out. Okay.
Right. So emphysema, high compliance.
Yep.
Cystic fibrosis, low compliance.
Okay.
Okay?
Yep.
Compared to normal.
Thank
Okay.
you.
Yeah, you're welcome.
Most of the people
Oh.
come Sunday day.
Great, thank you.
But there's the rest.
Okay, thank you, thank you. Yes.
One thing, I'm going to be gone next week, Wednesday through Sunday.
Okay,
Um,
I think Emily's going to be gone too. Are you
she's going to be gone Monday through Friday.
Okay.
She's going to Nama, and I'm going to California for Dairy Challenge with Marcia.
Okay, so I'm gonna try to, I really am gonna, let me go ahead and quit this. Stop.